This is Mr. Precella, and today we'll be reviewing square roots in an algebra class. And a square root symbol, if you look at your calculator, it usually looks like that. Let's suppose we have the square root of 25. Well, the square root of 25 is 5. Why? Because 5 times 5 is 25. It's what number can you square and get the number under the square root symbol. For instance, if we had something like square root of 49, we'd say the square root of 49 is 7. And so there are some squares roots that we know just from knowing the multiplication tables. Hopefully all of y'all have your multiplication tables memorized. And those are perfect squares. Let's write out the list of some of the perfect squares. Well, 1 times 1 is 1, but we won't bother writing that out. These are the numbers whose square roots we know just from the multiplication tables. 2 times 2 is 4. 3 times 3 is 9. 4 times 4 is 16. 5 times 5 is 25. You see right here, the square root of 25 is 5. 6 times 6 is 36. 7 times 7, 49. I think we'd already done that. 8 times 8, 64. 9 times 9, 81. 10 times 10, 100. 11 times 11, 121. 12 times 12, 144. It's getting harder, isn't it? We have the calculator. 13 times 13, 169. And, oops, 169. Let's just say dot, dot, dot. Those are the numbers whose square roots we know just from multiplication. The square root of 81 would be 9. These are called the perfect squares. Let's see, I'm going to be doing some homework problems or examples of homework problems. Let me pull up some of those. I've printed out some problems. And let's see, like right here. Problem number 1 says evaluate the square root of 121. Well, what number can you multiply by itself to get 121? Well, 11 times 11 is 121. Therefore, the square root of 121 is 11. Now, most calculators have a square root key on them. Okay, so if you want to get your calculator and punch in square root 225, that would be 15. If you want to check it, 15 times 15, is that 225? Well, yes, it is. So if the numbers are sort of large, you need to maybe use your calculator. Now, what about this one? How do we simplify a square root if that number under there isn't a perfect square? You see that 40? That's not one of the square roots we know just in our head, is it? We know the square root of 36 is 6. We know the square root of 49 is 7. So if we wanted a decimal number, I guess we could say that it's somewhere between 6 and 7. Well, here's how we're going to simplify this one. So I'm doing this problem number 3, simplifying the square root of 40. How do we simplify something like that? The square root of 40. There's a couple of ways to do it. One way is to draw out factor trees, and you may have done that in your previous math classes. The way I like to do it is just to rewrite the number under the radical sign. That's what this symbol is called, a radical sign. Rewrite the number under here as a product using one of these perfect squares, preferably the biggest perfect square. Well, what perfect squares divide evenly into 40? Well, there's not let's see, sometimes students say 2 times 20, but no, 2 and 20 aren't perfect squares. But 4 divides evenly into 40, doesn't it? We could think of that as the square root of 4 times the square root of 10, which we could then reduce by saying, okay, the square root of 4 is 2, and we can't simplify the square root of 10. There's no perfect square that divides evenly into it. So the square root of 40 is 2 square root of 10. See how I'm doing that? I rewrite it as multiplication. Like problem number 4, this next one, what's the square root of 75? Well, let's see, the square root of 75. Let's look at these perfect squares. I think there's only one of those perfect squares that divides evenly into 75, and that's 25. Is 25 times 3 45? 25 times 3 it's 25 times 3 75. 25 times 3 is 75. The square root of 25, I don't know if you can tell the colors here, but that's in blue. That's going to be a blue 5. This is a purple. Oh, the colors up there on the screen don't look so great with the projector, but hopefully you can tell that's a purple 5 square root of 3. So we say that the square root of 75 is 5 square root of 3. Now, the next one, problem number 5, says simplify the square root and all of that. Assume all variables represent positive numbers. There are no variables. If the square root is already simplified, state that. Okay? 51. Look at that. Think of our perfect squares. Do any of our perfect squares divide evenly into 51? If you have a calculator, punch it in. 51 divided by 4. That doesn't divide evenly. 51 divided by 9. Let's see. I'm using my phone calculator just so that it will show better on here. You can't be punching on your phone during a test. 51 divided by 4, no. I'm looking for the one. Is there a number that will divide evenly? And which numbers am I checking? These perfect squares. 59 divided by 16. No, another decimal number. 51 divided by 25. 2.04. So I just keep going until I either decide, okay, there isn't a perfect square that divides evenly into it, or I find one. If I get one that gives me an integer, like 75 here, when I went 75 divided by 25, notice I don't get a decimal number, 25 times 3. But for this 51, square root of 51, it's already simplified. You can't simplify that anymore. Okay? So the square root of 51 is as simplified as it's going to go. Now, let's look at problem number 6. The square root of 50. Let's see about that. Let's work that one out. What about the square root of 50? Square root of 50. Well, what perfect square will divide into 50? Well, sometimes students say 5 times 10, but no, 5 and 10 aren't perfect squares, are they? But 25 sure divides evenly into 50. So if we think of that as 25 times 2, hopefully the colors look better now. The blue square root of 25 will be a blue 5. The red square root of 2, that's as simplified as it'll go. 5 square root of 2. My red ink is dead. Okay. So 5 square root of 2. Let's write that down. So we're working with simplifying square roots. Let's see. Oh, here's a good one. Number 8, this next one. The square root of 360. If you want to start off with your calculator, keep in mind you want the biggest perfect square. Like if you start, 360 divided by 4. Well, yeah, that goes evenly, doesn't it? But I think we could find a bigger one. 9? Yeah, that goes evenly. Is there a bigger one? Oh, I'm here hiding. 360 divided by 16. Does that 16 divide evenly? No, that's 22.5. 360 divided by 25. And I'm just showing my calculator here just to try to show my thought process. My brain's running through this list of numbers, trying to figure out which is the biggest one that divides evenly into 360. And I think we've just found it, 36. We could rewrite this 360 as 36 times 10. A blue 36, a green 10. The square root of 36 times the square root of 10. The blue square root of 36 is just a 6. The square root of 10 is simplified as it's going to go. So 6 square root of 10. Let's see. Look at this one now. 45. Well, that's a smaller number. What perfect square divides evenly into 45? Well, how about 9? 9 times what would give us 45? 5? 9 times 5 is 45. So this blue square root of 9 becomes a blue square root of 3. I mean, it's a blue 3. Square root symbol going on the blue. And then square root of 5. So 3 square root of 5. This is just do my math lab assignment, or my math lab assignment that I printed out. And so we're actually doing this live on my math. I'll be punching in the answers. Ooh, 208. Let's see. That's a bit larger. Maybe this is one of the ones where I want to use a calculator. Let me get my calculator. Clear. Okay, so 208. So I'm going to start. 208, well, divided by 4. Yeah, 4 times 52. I'm just going through. 9, no. Why am I saying no? That was a decimal number. 208 divided by 16, 13. So 16 times 13 would give me 208. Let me just check that out. 16 times 13, yes, that's 208. So what I could do is rewrite this as the square root of 16 times the square root of 13. Now, what purple number am I about to write? I have a purple square root of 16. Well, the square root of 16 is a purple 4, and then square root of 13. Okay? So 4 square root of 13. Let's see now. Number 11, 250. Well, let's see. What perfect square divides evenly into 250? Well, if you look at these perfect squares, probably you can pretty quickly figure out 25. 250 divided by 25. If you want to punch it into your calculator, okay, I think I'll just write it as 25 times 10. Hopefully you'll trust me on this. 25 times 10 is 250, and there's no bigger perfect square. If you divided 250 by 36, 49, 64, 81, or 100, you're going to get a decimal number, not a whole number. So thinking of 250 is 25 times 10. The square root of 25 is 5, and then the square root of 10. So 5 square root of 10. Now, the next problem is a little bit more involved. It involves two square roots, multiplying two square roots together. To multiply square roots like this, you just multiply the numbers under the square root together. So you'd say square root of 2 times the square root of 28, times the square root of 14 is the square root of 28. Okay? But don't stop too soon because you're not really finished yet. The square root of 28 can be simplified. You simplify square root symbols just like you simplify fractions. You always got to make sure you simplify them. Don't leave that square root of 28. Well, how do we simplify? Well, that's what we were doing up here. On 28, what perfect square divides evenly into 28? Well, 4. 4 times 7 will give me 28, won't it? 4 times 7. And so, oops. So this is a blue 2. Why? The blue square root of 4 is a 2. The square root of 7 can't be simplified. So you'll type in 2 square root of 7 as your answer here. Now to multiply square roots together, you multiply the numbers under the square root together. Now before we do number 13, I want to think about something first. Let's do number 13, but with smaller numbers first. Notice, here it has 23 and 23. Those are a little bit bigger numbers than 2 times 14. Most of us can't just multiply 23 times 23 in our head as fast as we can say 2 times 14 is 28. But let's think like this. I'm just making up a few problems. I want to see if y'all will notice a pattern. Let's multiply. Suppose there had been the square root of 5 times the square root of 5. Well, you multiply the 5's together to get a 25, but that can be simplified. The square root of 25 is 5. I'm looking at problems where the number under both square roots is the same, just like on number 13. They're both 23. Suppose we'd had 9. The square root of 9 times the square root of 9. That would be the square root of 81, which is what? 9? Is there a pattern here? Y'all see it? Let's see, what about this one? The square root of 12 times the square root of 12. Well, 12 times 12 is 141. And what's that square root of 141? It is 12. Y'all see the pattern I'm talking about? The answer here, if you have the same number under both square root symbols, then you could skip this step right here and just go straight to this. The square root of 5 times the square root of 5 is 5. The square root of 9 times the square root of 9 is 9. During that problem, we're going to have to do square root of 23 times the square root of 23. We can do that without actually multiplying the square root of 23's together and just write what is the answer. 23. The square root of 23 times the square root of 23 is 23. Now, let's write this as a rule. Is that always true? Yes. Here's a rule. The square root of a times the square root of a, if these numbers are the same numbers, the square root of a times the square root of a is always a. Okay? So if we wanted to figure out the square root of 38 times the square root of 38, you don't actually have to get out your calculator and multiply out 48 times 48. What do? You just say, okay, it's 48. And you can convince yourself of that if you just do it with smaller numbers. Like the square root of 2 times the square root of 2. Well, 2 times 2 is 4. The square root of 4 is 2. So you don't need to show that step. Okay? With those. Now, there's another way this rule could be written, and we'll see that popping up. Another way you could write this rule, something times itself means squared. So we could write it like this. The square root of a squared is just whatever's underneath that square root symbol. And that little rule is going to be popping up throughout the semester. It always pops up in algebra. If you square a square root, you're just left with what's underneath there. Okay? Let's see. Let's do some more problems. Look at this one, number 14. It's no longer doing square root of a times square root of a. There's different numbers under here. So you're actually going to have to go through. 3 times 6 is 18. Now let's think about how to simplify square root of 18. I think I heard it. What's the square root? The biggest perfect square that divides into 18. That is 9. We could think of 18 as 9 times 2. What's the green number going to be? 3 square root of 2? 3 square root of 2. So to multiply square roots, you multiply the numbers under the square root together. Okay? Be careful. On 15 and 16 and 17 and 18, these next 4 that we're doing, it's adding and subtracting. To add or subtract, you just add the numbers in front, or subtract, whatever the case would be. 7 square root of 2 plus 3 square root of 2 is 7, excuse me, I said it wrong. 4 square root of 2 plus 3 square root of 2 is 7 square root of 2. When you're adding and subtracting square roots, don't add the numbers underneath it. Okay? Like on number 16, 2 square root of y plus 6 square root of y. That's a 6 there. It might look like an 8, but it's a 6. 2 square root of y plus 6 square root of y is, I'll write the answer right here in this blank. What should I put there? 8 square root of y. Okay. Now, number 17. It's addition and subtraction. So you're just treating this as if it were just some variable expression. 7x minus 6x plus 4x. In college algebra, or in algebra, we always talk about combining like terms. That's what you're doing. You're just adding these numbers in front. 7 minus 6 or if you want to think of it as 7 plus a negative 6, but 7 minus 6, most of us know that's 1, plus 4 is 5. Do I add the numbers under the square root symbols together? No. Leave it as 5 square root of 7. I have a feeling a very common wrong answer here might be, well, I don't know, something about a 21. Would a 21 pop in or not? All I'm doing is just adding the numbers in front. 7 minus 6 plus 4. Okay, that's a 5. And then keep the number under the square root. Let's write that out. To add square roots, add the numbers in front of the square root, the numbers attached in front of the square root. Oh, I'm sorry, that's my habit, cursive writing. I've been trying to get out of it, that habit, for a long time. To add square roots, add the numbers attached in front of the square root symbol. Do not add the numbers under the square root. The numbers under the square root symbols are called radicands. Okay? Do not add the numbers under the square roots symbols. Just leave those alone. Okay? Just leave them as they are. Okay? 2 square root of y plus 6 square root of y, 8 square root of y. 4 square root of 2 plus 3 square root of 2. You add the 4 and 3. To get 7 square root of 2. Don't add those 2's to get a 4. On number 18, it's getting a little messier. 2 square root of 8 minus 2 square root of 2. On number 18, we don't have the same number under both square root symbols. That's what we need. We need the same number under both square root symbols if we're going to add or subtract them. And so I'm going to work out this problem right here. 2 square root of 8 minus 2 square root of 2. Well, there's some simplification we can do on here first. This square root of 8 can be simplified the same way we were simplifying the square root of 40 by writing it as 4 times 10. Let's see, square root of 8. What perfect square divides evenly into 8? Well, a 4. Okay, so I'm going to think of this square root of 8 as the square root of 4 times the square root of 2. We still have this big purple 2 right outside here. Again, you may not be able to tell the colors up there on the display. So we have a purple 2, I'm just carrying down. This blue 2, this blue square root of 4 is a blue 2. And we have the green square root of 2. So this 2 square root of 8, we could simplify all of that down to what? We could simplify that down to a 4 square root of 2. So the problem, 2 square root of 8 minus 2 square root of 2, is actually 4 square root of 2 minus 2 square root of 2. Now, do we know how to subtract those? Well, yeah. Now that we have the same number under both square roots, just do what we did on these. 4 minus 2 is 2, and keep the square root under there. So 2 square root of 2 is our answer. Now, there's one more thing we need to discuss before we call it quits here, and it's something called rationalizing a denominator. You never, ever, ever want to leave a square root in the bottom of a fraction or a denominator under a square root. This problem number here, number 19, I'm going to show you how to do what's called rationalizing the denominator. By the time we're through with it, there won't be a denominator under the square root. There won't be a square root symbol in a denominator. So here's the one we're going to do. Okay. This is something called rationalizing a denominator. Rationalize a denominator. If we have something like this, the square root of 10 over 7. What we're going to do is think of that as, since the symbol is over both the 10 and the 7, I'm going to go ahead and write it like this, as the square root of 10 over the square root of 7. And what I really want in the bottom is just a 7. I don't want the square root symbol. So what I'm going to do is multiply above and below by the square root of 7. And you'll have a square root. Remember, when you multiply the numbers underneath there. The 7 times 7 is 49. But we don't need to use a 49 because we have that rule. A square root times itself is just whatever's under there. So 70 square root of 7, square root of 70 over 7. When you're rationalizing a denominator, you're rewriting it so you don't have a square root symbol in the bottom anymore. If you're told to rationalize a denominator, you're just going to multiply above and below by the square root that's in the bottom. Like 20 is probably a better example. Because, I don't want that square root of 3. So multiply above and below. You know what? That's so small. Let me write it out here. 9 square root of 7 over 7 square root of 3. You multiply above and below by the square root that's in the bottom. Now, the 7 times 3 is 21, and just stick that 9. Keep the 9 and say 9 square root of 21 all over. Now here it gets a little tricky. The square root of 3 times the square root of 3, we don't need to write that as a square root of 9. We can just go and say the square root of 3 times the square root of 3 is 3. So on the bottom we have a 7 times 3, which is 21. Notice we no longer have a square root in the bottom, which is what we wanted. And we can now do a little bit of canceling right here. The 9 and 21. Just reduce that as you would any old fraction. Divide both of these numbers by what? 3? So you'd have 3 square root of 21 all over 7. And that's called rationalizing a denominator. Okay? So if someone tells you to rationalize a denominator, just whatever the square root is in the bottom, multiply above and below by it. Okay? Well, we are out of time right now, so I'm going to call it quits and say thank you for watching. We've been discussing simplifying square roots, working with square roots. In preparation to starting college algebra class, these square roots will be popping up all semester. So this was a nice little review of them. So thanks for watching, and I will be talking to y'all later. Bye-bye.